Last time we saw one of the most relevant services of online providers, which are recommending systems. Today we will go forward in probably the most rich market, or one of the most rich markets in the web, which makes clear how providers such as Google makes money, which is the web advertisement. So this is one possible graph that you would find on the internet about the market. Now, I think the two most relevant information is that we are talking about possibly hundreds of billions of dollars, so really a lot of money. And the other interesting part is that the trend is exponential over time. So clearly this is one of the most significant revenues for web service providers and for Google in particular. Okay? So the idea today is to try to have a first understanding of what are the technical ingredients in order to support this market. Okay, as usual, as we did last time actually, we are going to use the material available at Stanford. And so again, those are the two links I gave you also last time. Plus, this is a, sorry, this is the old one maybe, 1 second. No, I made a mistake. Plus, there is a link to a website which gives you some more detailed information about the market, but we will see it later on. Okay, so in order to define the framework that will allow us to analyze the technical ingredients to support some of the functions necessary to implement the web advertisement, we need to understand the difference between the classic model of algorithms and the online ones. Okay? In the classic model of algorithms, when you analyze the performance of the algorithm, usually you have the whole input known. Okay? So this is why you are talking about offline, because everything is known since the beginning, and then you compute a given function in order to see what are the performance, okay, in time, in space, or even in terms of more general concept of cost. Okay, in online algorithms there is something different. The idea is that the input is not known in advance. Okay? You observe the input step by step, and what happens is that your algorithm has to take decision about the input only on the basis of the past history, because it does not know the future. Okay? It doesn't know the whole input. It only knows the fraction that has been already seen, and it has to take a decision about the current input. Good? Okay, so we will see why we are talking about online algorithms. First of all, what is the idea here? The idea is that in this picture you see something. Assume that you have a given query on a search engine, and you probably know that you have the sponsored links, right? What are those sponsored links? Are people that basically pay in order to appear in that query, because they do believe that their content, their advertised content, is relevant for the query. This is the idea. Okay, so basically you have a number of queries, and then here you have advertiser, namely organizations that are interested in providing an advertisement for that given query. Okay, and as you see, you have a kind of clusterized structure. If you have this graph of the advertiser query, in which you have some clusters. One of these is gambling, the other one is sports betting that clearly is a subcluster of the more general concept of gambling. Okay, but this is the idea. Okay, so what happens? Why we are talking about an online algorithm? Because basically, queries are appearing over time because users are making a specific query, and you have to select which advertise to show on the web page. Only on the basis of the past queries and the current one, but you don't know the future. Okay? That's why we are talking about an online algorithm. Okay, so basically you can formalize this problem as a graph matching for advertisement, in which on the left you have the advertiser, on the right you have a given query that is of interest for the advertiser, and thus it's something that and this means that the advertiser would show up his advertisement as a result of that query. Okay, and clearly what happens is that you might have that the advertiser are interested in different queries, and at each instant in time you have to assign a matching between the advertiser and the query in order to show up that advertisement. And most likely you will get back money that advertiser will pay for this. Okay? So the idea is that we have to make decision on which query we have to show, and we don't know what will happen in the future, what kind of query will be done by the users in the future. That's why we only know a limited amount of information. Okay? Okay, we need a bit of background about online bipartite matching. So this is an example of a bipartite graph in which you have basically boys on the left and girls on the right. Okay, and then there are links that basically represent a kind of connection, a relationship between a boy and one or more girl, or vice versa. Okay, and what you want to do is you want to match the boys to girls that the most preferences are satisfied. Namely, you want to form couples between boys and girls so that each boy will be matched with a girl, and possibly none of the boys and none of the girls will be without a partner. That's the whole idea of the graph. Okay. Clearly, even in this, is this an example of online or offline problem? This is offline. We already know the graph. We have simply to select the arcs. That's it. There is nothing online here. Okay? And one possible matching is the ones that is represented in this picture. Okay? And in this particular solution, we have basically that the cardinality of the matching is 3, are the 3 bold edges. So question, can we do better?
Not always.
Yes, not only in this instance, I mean. Yes, clearly we can do better. So as an example, you have this solution in which the cardinality is 4, okay? Okay, is it clear that once an assignment has been made, you cannot assign the same boy or the same girl to another couple? Okay, that's the constraint. Sorry, maybe I was not clear about that, but this is the constraint. Okay, so this is another possible instance of this solution for the problem, and clearly here you see that the cardinality is now 4. So it's much better because basically we are satisfying all the nodes in the graph. Okay, so basically we call perfect matching when all the vertices of the graph are matched. So in this particular case we have a perfect matching. Or we have a maximum matching that basically means that the maximum number of, largest possible set of matches is provided, but is not the same cardinalities of the vertices. Okay, good. Now, this problem clearly has an offline solution, but we are more interested when we are talking about as an offline solution, but we are more interested when we are talking about an online solution, because as we said before, the new queries are not known in advance, right? Because basically users are putting queries and we want to associate those queries to an advertiser. Okay, so they appear over time. So we are interested in the online version when vertices, namely the queries, and edges, namely the advertisers possibly interested in those queries, appears over time. Okay, so in this case, the online problem of boys and girls matching is that we have initially a set of boys. So basically, here we have the set of boys that is known in advance. What happens is that at each round, a girl will appear, providing the possible matching. And at each instant in time, we have basically two options. Either we pair the girl with a boy, according to the possibilities. So I don't know, it can be this one. Or I cannot do, or I will not do anything. I will not take any decision. I will defer the decision. Okay, two options. Okay, this is clearly an example of assigning tasks to server. Tasks are not known in advance. They will appear over time. Or is also an example of assigning a query to advertiser, okay, as we saw before. Okay, let's see. What happens in this case, assuming that the girls will appear one after the other. So at the beginning, the girl A appears, and you have two options. Either is connected with 1 or with 4. And in this particular solution, assume that we select this link. And so we have 1A as the first match. Then B appears. We have those two options. This has been already selected. Huh? So we select this one, and so we have 2B. Then C appears. Notice that C has only one option. It's connected only to 1. But since 1 has been already matched, we cannot do anything. Okay? And finally, D appears, and we can connect 3 with D. Okay? This is one possible example of an online instance in which basically what happens is that, first of all, not this one. At instance 1, you have this option, and you select this one. At instance 2, you have this option, and you select this one. At instance 3, you have this option that can go only to this node here, but since it has been already matched, you cannot do anything. And finally, at instance 4, so you see they appear over time, instance 1, 2, 3, and 4, you have this possibility, and actually you can assign it. Okay? That's it. Good. So is this clear, the difference between online and offline? Okay, good. So what can we do? Okay, one possibility is to use a greedy algorithm. And the greedy algorithm is very simple. When a new girl appears, what you do is you match it with any eligible boy. What is an eligible boy? A boy that is linked with the girl and has been not already matched with any other girl. That's the whole story. Okay, so the question is, how good is the algorithm? How can we estimate the performance of the algorithm? Okay, in this case, in the case of all-line algorithm, the technique to evaluate the performance of the algorithm, one of the possible options is the competitive ratio. What is the idea of the competitive ratio? You are going to compare your all-line algorithm with an offline optimum, namely an optimum that knows all the input in advance and can basically provide the best possible solution. Okay? So notice that we are comparing something that knows the whole input in advance with our all-line algorithm that has to take decision when input appears over time. Okay? Good. And so what you do, and on all possible inputs, so you are not considering only a specific inputs, on all possible inputs, the competitive ratio is the minimum of the performance of the optimum that knows everything and our algorithm. Okay? This is the idea of competitive ratio. Is this clear? So to some extent we are saying, if somebody knows everything, the optimum can do this at best, and the competitive ratio is on all the input, what are the performance of my algorithm with respect to this optimal guy. So since here we have the minimum, what is the greedy worst performance over all possible inputs? This is a lower bound. Those are the worst performance. Okay. Good. So let's analyze the greedy. Okay, let's assume that greedy, the performance of greedy are different from the performance of the optimum. Okay, good. So now, in blue, we have the solution of the optimum. In red, we have the solution of the greedy. And let's consider the set G of the girl that are matched by the algorithm, by the optimum, but are not matched in the greedy. So this exists because greedy is the cardinality of greedy is different from the cardinality of the optimum, and by definition, the optimum is the one with the best performance. Okay? Okay, so G is this graph. Okay, so by definition, clearly, the solution of the optimum is less or equal of the solution of the greedy plus G, because basically we are putting, to consider the optimum, we have also to consider something that has not been considered by the greedy, okay? Something that is not part of the greedy solution. Okay, so this is the first equation. Is this clear? In this case, because
why not equal? And greedy plus G should be all.
Because you might have more than one node that is in G, right? Okay, and okay, sorry, it should be equal. I'm not sure. No, it should be less or equal. Wait, I have to think about it. Anyway, in the solution is exactly the same. Let's assume it's less or equal, and then we'll see. Okay. So now, the boys B are the ones that are possible links for the girl. Okay, that is the ones in G. So basically, in this example, what are the boys in B are those two. Okay? Does this make sense? Is it by definition? Okay. Note that the boys in B are already part of the solution by greedy, because otherwise they will be added, right? Because if they are not part of the solution in greedy, since this is connected to those two boys, I could add it to the solution. Okay? They have already a match in greedy. Otherwise, since they are both connected to the girl, I would add it to the solution. But I'm not adding it because, by definition, G has not a match. Okay? Is this clear? Okay, so, again, M greedy is at least SB. Okay, good. Okay, so if we put together those two first ingredients, we have those two equations. So now we observe that optimal matches all the girls in G to some boy in B, because greedy cannot do it, but the optimum, by definition, has to consider all the elements and thus will do this matching. And so we have that the cardinality of G is less or equal to B. Namely, I need an option in order to connect. At least one option. There could be more than one. That's why it's less or equal, but at least I need an option. Okay? So if I put here this, then I have this other equation. And so putting all together, we have that the cardinality of G is less or equal to the cardinality of M greedy. Okay? Good. So now we are putting all together. And basically, we simply are going to put 4 into 1. And so basically we have that M optimum is less or equal than twice M greedy. Okay? We are putting this there. And so now, if we want M greedy over M optimum, this is greater than 1/2. And then with those, and so we prove that actually the greedy algorithm has a competitive ratio of 1/2. Okay, I will get back to your question, but now I have to think about it. Okay? Good. Now, actually, there is also, this is the lower bound, because we didn't make any assumption on the input, right? So this is true for any given input. Since it is true for any given input, it is also, it gives us the competitive ratio. Okay, now, is this also an upper bound? Namely, are there examples, instances in which actually we get 1/2? And this is an example of an instance in which we get 1/2 because A appears and I connect it to 1, B appears and I connect it to 2, and then I cannot connect neither C nor D because they have been already, the matching from 1 and 2 have been already assigned. And so this is an example of an upper bound. So this is both lower bound and upper bound is 1/2. Okay? Good. So let's see a bit more what is the connection of this bipartite graph with the web advertisement. And let's start with a very short introduction on the history of the web advertisement. At the beginning, basically, we have a static advertisement. So the idea is that I will show up an advertisement, and simply for the fact that I will show up it, you as an advertiser has to pay me some amount of money. Usually it was this CPM, cost per 1,000 impression. Notice the word impression. Impression does not mean that somebody would click on it, but simply that you show it. Okay? Okay, clearly the problem is that you are going to show this stuff from untargeted users, so you don't know how to select when to show this advertisement. It was very ineffective. And so the next question is how to actually target this information to somebody that at least in principle could have that interest. And so what is a possibility here is to use the query given by the user in order to understand what are the interests of the user in that time. Okay? And so possibly you can use this information in order to improve the quality of your advertisement. Okay? Make sense? Good. So this allows to pass through, to pass from the CPM, so from impression to click, really click. Indeed, the main problem is that the click on this approach, on this initial approach, were very low. And so the return on investment for the advertiser was relatively interesting, because the advertisement was not targeted. Okay, so this another search engine that existed I would say at the beginning of the internet, this Overture in 2000, had this idea of allowing advertiser to make a bid, as we said before, on search keywords. Namely, say, okay, I am a sport, my business is on a sport. I will pay a given amount of money if a user will search a sport term in order to show my advertisement. This is the idea. In this way, we can pass from uncategorized users to categorized one using the query as a proxy in order to figure out what are the interests of the user. Okay? And so, thanks to this, the important part is that basically you are able now to evaluate not only the impression, but you are also able to evaluate the effectiveness of your system through the real click that the users will do on the advertisement. And this is the main idea of the AdWords. So the main idea is that you can bid for given keywords in order to show up your advertisement, and then now you can pass from impression to click-through. Okay. Okay. This is an example of the sponsored links that can appear. Okay. It works very well indeed, and this is a very rich market. There are a number of interesting problems from the perspective of the search engine and from the perspective of the advertiser. Today we will focus only on the perspective of the search engine, and basically given a query of a user, what advertisement should I show in order to maximize my profit? This is the main idea, because I remind you that advertisers are doing bids, namely are offering money in order to appear in a given query. So what should I select? Okay. Okay, before going to the problem, I just want to show you very quickly this website, in which basically you have a kind of overview of 2018 situation. And now it's not very clear, but you have two distinct areas. One is the search areas, that is the one we were talking about, namely I write down a query and I provide advertisement for that given query. And the other one is the Google display network. In this case, the idea is a bit different. You anyway make a bid for a given query, but instead of providing the advertisement on the search engine, what happens is that you get the advertisement on a number of websites, millions of websites or mobile applications that are related to that term. Okay? So if you have, I don't know, a new application on the Android market, which is, again, related to sport, and sport is one of the tags, if you make a bid on the Google network, you can Google Display Network. So basically, your message, if matched, will be displayed on a number of websites or applications. Okay. So this is for different sectors, and you see the number of click-through. What do I mean by click? What do we mean by click-through? It means that not only I show you the advertising, namely I show you the picture of or the advertisement on the search engine, but also that you click through. Namely, the user will click on it, not simply have an impression, but also click. Okay, and we're talking of something that goes around. This is 1, 2, 3, from 1 something percent to 3 something percent. Okay, just out of curiosity, this is the dating sector. So apparently, this is the most successful click-through sector. And you have quite different percentage in the Google Display Network, and which are at most, say, 0.5%, and in some cases they reach less than 1% in this particular case, which is actually technology. Okay. Not only this gives you an idea of what are the click-through, but what is interesting is also the average cost per click. And what I didn't know much about that, but the cost is up to, say, almost $6. It is in average 2.32 in the search part, and is up to almost $1.5 and in average $0.58 in the display network. Okay, so this is and this motivates the multi-billionaire market. Okay, now let's formalize the Adwords problem, and let's focus only on the search engine in this particular part. So you have a stream of queries that arrives over time to a search engine, so users that are given the query. And then you have that several advertisers bid on each query. Namely, they say, okay, if the query will be about, I don't know, sport, again, I will pay this. If it's about technology, I will pay that, and so on and so forth. You have a bidding. So when a query QI arrives, you have to select a subset of the advertiser that you want to show to the user. So depending on the number of sponsored links that you allow in your system. Okay? Clearly, from the perspective, and here I remind you that we are from the perspective of the search engine, the main goal is to maximize the revenue. Because, as I told you, advertisers will pay, and you want to maximize the revenue. Okay? Okay. And this is an online algorithm. Why is an online algorithm? Because the query will appear over time. You don't know the query in advance. Okay. So let's see one possible solution. So the solution that seems to be the simpler one is a solution that takes also only into consideration the bid, right? So if the advertiser A will bid $1 and the advertiser C will bid 0.5, the simpler solution is the one that will assign the bid to the advertiser A. Unfortunately, this solution, why? Because it's the ones with the highest bid. Unfortunately, this solution, it does not take into consideration that, but it also depends on the click-through rate, namely how many times people will click on it, not only on how much they will pay, okay? So if you put together the click rate and the bid, now, as an example, here, you bid $1, but only 1% of the advertisement will be actually clicked, and so you get 1 cent as a revenue of the search engine. If instead here the bid is less, but you have 2.5% of the click-through rate, so in this case you have 1.25 cents, and here you have 1.5 cents. So the idea here is not sufficient to take also into consideration the advertiser that made the highest bid. You have also to consider how many times likely users will actually click on the advertisement. Okay. Okay, so what you can do in the strategy in which you only consider the bid, you have a ranking. In the strategy in which you have the expected revenue that can be calculated by the bid multiplied by the click-through rate, you get a ratio, sorry, you get another another ranking, sorry. Okay. The main challenges that you have are basically two. Is that, well, the CTR is not known in advance, and so the question that you have to answer is how to estimate the CTR, which is not known. And then that the advertiser have a limited budget. Okay, so they give you not only how much they would pay for a given query, but also they have a budget, and you want to respect this budget. You cannot basically assign all the query to only a single advertiser, otherwise you will go over the budget. Okay, the idea is that with respect to the budget is that the search engine will guarantee that each advertiser will not charge more than the daily or hourly or yearly or whatever it is budget in a given amount of time. And in order to predict the CTR, to have an estimation of the CTR, what you can do is you can have a kind of log of the previous query, and you can predict it historically. So basically you can some statistics in order to get information about the expected CTR for a given query. And we will see very quickly that there is a problem, because what is the problem? To some extent, you would like to show to get information about new terms. And so in the matching problem, you want to show new terms. So to the other, you want to exploit the information that you already have. So we will see later on that this is a problem. Another problem which is relevant, and there is a graph that shows it clearly, is that CTR is also position dependent. It's not only query dependent. We saw that the sponsored links are anyway one of the others. We already know from the search engine that the position of a response is strictly related with the probability that people will click through, and this is true also for the advertisement. So CTR should consider both the query and the position of the advertisement. Okay, and this is the problem I told you about. It's called exploitation versus exploration versus exploitation. To some extent, we want to build a story about a given query, and so we want to estimate the click-through. At the other time, we should show something that we already know, something that for which we already have the statistics. So there is this trade-off between building the statistics on the CTR or exploiting the already available statistics. And this is something that must be taken into consideration. Okay. Okay, so let's put together all these ingredients to have a more formalized Adwords problem. Okay. For the search queries, we have a set of bids made by the advertiser. So again, I am a company interested in vending, in selling sport equipment, most likely, or I don't know, soccer balls. So if the word soccer balls will appear, I will make a bid in order to show up my advertisement. Okay. Now, for each advertiser query pair, we have a click-through rate, and we know that we have this issue on how to build this click-through rate, but now let's pretend that we have the click-through rate. Each advertiser has a budget, so we cannot basically not consider the budget and give all the query pair to a single advertiser. And then we have also a limit on the number of advertisements that can be displayed for each search query. Okay, I cannot show thousands of advertisements, otherwise it's ineffective. So what we want to do is we want to select as the provider of the search engine service. We want to respond to each search query with a set of advertisers, people that will pay the bidding, so that the size is not larger than the limit of the query, because we want to show up an advertisement for each advertiser that will not be more than the allowed allowed ads. Each advertiser has bid on the search query. Clearly, if it will be showed up, it means that he is interested, and that he or she is interested, and thus he made a bid. And the advertiser has enough budget in order to pay the advertisement. Okay, this is the general setting. Okay. Okay, let's consider a simplified scenario environment. So basically, there is only one advertisement for each query. Okay. All advertisers have the same budget B, so this is fixed. All ads are equally likely to be clicked, so I do not have to consider CTR in this particular case. And the bid value is the same for everybody. So it's a very, very simplistic scenario, but that's just to model and understand what's going on. Again, we can consider the greedy algorithm, and since we have one ad shown for each query, it means that basically for each query we are going to select only one advertiser, and this is basically, if you think about it, very similar to the greedy algorithm that we saw for matching boys and girls, because we have to select only one arc connecting. If we want to show up this advertisement, only one arc among all the possibles that will connect query to advertiser. Okay, and so it should be not surprisingly surprising. It should be not a surprise that we have a competitive ratio of 1/2, because it's basically the algorithm that we discussed before. Okay, so the question is whether we can do something better with a different algorithm. We know that greedy has a performance of 1/2, competitive ratio of 1/2. The question is, can we design another algorithm that will perform better, and how much better? Okay, and this is and we will go through the definition of this algorithm considering a few examples. Okay, let's assume that basically we have now that the advertiser A bids only on the query X, while the advertiser B bids both on the query X and Y, and the budget B is equal to 4. And I remind you that we pay 1 for each advertiser. So, assuming that the query stream is X, 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 Y, 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 okay, the worst case choice by the greedy is that I will always select B for the first 4. And since then, Y cannot be selected by A because it didn't bid on Y, basically I cannot assign the last 4 Y query. Okay? Does this make sense? Again, A bids only for X. B bids for both. Greedy algorithm means that when I see the input, I assign it in a greedy way. I will select one that can be assigned without any other choice, any possibility. Okay, so the worst case is that I will always select B. If I will always select B, it means that when the Y will appear, basically A cannot be satisfied because he only bid for X. And so there isn't an assignment, while clearly you can have this assignment which is optimal. Okay? So the competitive ratio is 1/2, as we expected. And this is one of the example. Okay. Good. Do you have any idea of what can you do? Now, the greedy algorithm is something that basically say, if I can assign to somebody, I will select somebody. That's it. It doesn't take into consideration anything else. Now, can we design something that is a bit more, say, a bit smarter? What is the problem here is that we basically elapsed all the budget, and we cannot guarantee any other option for A because it didn't bid for Y. So what could be a possible idea? Constraint on what? Yeah, that's true. Instead of taking any possible choice, we have to say define a policy to make the selection. What kind of policy? One possible, let's see. The idea is the balance algorithm, in which basically each time I do the following. For each query, I pick the advertiser with the largest unspent budget. Okay, so this is the constraint. Largest unspent budget. Okay? The idea is that through this policy I can balance the load in terms of query associated to each advertiser according to the remaining budget. that is consumed over time. Remember that we are still in the model in which every advertiser has the same budget. Okay? But over time, the budget will change, right? At each instant in time, each advertiser consumed some of this budget, and so has some unspent budget, and I will assign the query to the advertiser with the highest budget. That's the idea. Okay. In case you have the same budget, so you have a tie, break it in any way. I don't know, select the advertiser that has not been selected in the previous step, or something like that. You can have any arbitrary but deterministic policy. It's up to you. This is the idea. Okay. Let's see what happens here. So the query stream is as before, x, 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 y, y, y. The budget is 4. Now, let's see what happens. Okay, say that if you have a tie, we break it taking the advertiser with first in the lexicographic order, so A. Okay, so beginning, x appears, both have 4. We have to break the tie, we take A. Okay, A. Second, x appear. Now the budget of A is not anymore 4, but is 3, while the budget of B is 4, and so B. We break the tie A, B. Now, Y cannot be assigned to A because it didn't bid, and so necessarily we have to assign it to B, and then we have to assign it to B, and then those will not be assigned because we finished the budget of B. Okay? But notice now that instead of 1/2, we have 3/4. Okay? So it's indeed better. We can do better with this simple algorithm. And we can consider the idea, we can consider this idea and give a simple analysis that actually show what is the lower bound, and let's see. So in this case, we have 2 advertisers, A1 and A2, each with a given budget B, which is greater or equal than 1. Okay? The idea is to prove the lower bound, and that is that the optimum solution exhausted both the advertiser budget. So if the budget is B, it means that the optimum is 2B, because basically it used both the budget. And so notice that here budget and the number of advertisement placed is the same thing, because we pay 1 for each advertisement placement. Okay? Okay. What happens is that if we consider the two advertisers, A1 and A2, there must be an instant in time in which the budget of one of the two has been exhausted. Because if this is not true, we can now allocate more query to that advertiser. We can proceed, but at the end, at least one of the two will reach first the allowed budget, and so it will be exhausted the budget, while the other has still some budget to be spent. Okay, the argument is simple, because if this is not true, I can still allocate budget. But eventually, over time, at the end, I will allocate all the budget of one of the two. Okay, and now let's assume, for the sake of simplicity, that the budget of A2 budget is exhausted. Okay, so we are now in the situation in which we know that the optimum is to B. We know that one of the budget has been exhausted, and let's see what can we say. Okay, so let's analyze the algorithm with this picture. So we have that if we consider the optimum, the blue queries are the ones that have been allocated to A1 in the optimal solution, and the green queries are the ones that have been allocated to A2 in the optimal solution. As observed, the optimum revenue is now 2B. I have allocated all the possible query. So what is the revenue of the balance algorithm? Namely, how many query has been matched by the balance algorithm? Okay, clearly it is B, because we say that A2 is exhausted, and we know that the balance is B, plus what has been allocated to A1. Okay? So we have balance budget is equal to B. Why B? Because of this, A2 exhausted, and so we have allocated all the budget, plus Y, which is what has been allocated by A1. Okay? Good. Now, so basically what we want to prove, and we write it here, is that Y, this is the goal of our analysis, is that Y is greater or equal than B over 2. Okay, let's see whether we can prove it. Okay, we have basically two cases. The case that more than B over 2 queries have been allocated to A1. Okay, case number 1. Okay, if this is true, the fact that Y is greater or equal than of B over 2 is trivial, because basically it's what you can see from the picture, right? So case 1 is trivial. Okay, the case 2 is that more than B over 2 of the blue queries have been associated to A2. Okay, this is a bit more tricky, but let's see what can we say. Okay, so let's consider say the blue query that is here, the last one that has been accepted by A2. Okay, we have the last blue query that has been accepted by A2. Okay, so consider the last blue query assigned to A2. When we make this assignment, we know that A2 unspent budget must be at least as big as the one of A1. Why? Because the balance algorithm will assign the new query to the advertiser with the greatest budget. So if has been assigned, or it has to break the tie, right? So it must be at least as big as A1. Has been associated here, it means that Y has been selected A2, because the budget is at least as A1. Is this clear to everybody? It's by the definition of the balance algorithm. We are assigning a query to the advertiser with the highest residual budget. Okay, so it means that this is the ones with the highest residual budget, so it means that is at least as A1. Okay? Which means that at least as many queries have been assigned to A1 and to A2 in that moment. Because it at least has. And so, by this, we can say that we have assigned at least B over 2 queries to A2 because of the initial hypothesis of case 2. Okay? And so again, we have Y that is bigger than B over 2. Okay? Good. So, now we have that balance is B plus Y. But now we know that Y is bigger than B over 2. Okay? And so we have B plus B over 2. And so 3 over 2B divided by 2B, which is 3 over 4. Okay? And so we prove that actually the performance of the balance algorithm in this case are 3 over 4. Okay, it's a simplistic case, true. We are in a very specific situation, but anyway, this is 3 over 4 that is much better than 1 over 2 that was the greedy algorithm performance. Okay. So it can be proved. We are not interested in proving this, that actually in the general case, the worst competitive ratio is 1 minus 1 over E, which is roughly 0.63. This is in the general case with all the assumptions we made in the general model, namely the budget is not the same for all the user, for all the advertiser, they can bid, etc., etc. Okay, so and what is nice then is that no line algorithm has a better competitive ratio. Okay, so balance works pretty well, and is indeed a very good performance algorithm. Okay, good.